Hi everybody, today's lesson is Chapter 4 and the title is Optimization. The first thing I'd like you to do on your note sheet is copy down the definition I've written right here on optimization. It's the action of making the best or most effective use of a situation or resource. So feel free to pause this video and get that definition down. Okay, underneath the definition, optimization is just another application of the derivative. So let's take a look at example 1. I'm just going to read it out loud. An open top box is to be made by cutting congruent squares of side length x from the corners of a sheet of construction paper. Once the squares are cut, we will bend up and tape together the sides to form a box. The question is, how large should the squares be cut to ensure that the box holds as much as possible? What is the resulting maximum volume? So we're optimizing the volume of this box. We want this box to hold the most. So we are looking for the box of maximum volume, and we want to know how large we should cut these squares from the corners in order to make that happen. So let me sort of demonstrate. We're going to do this in class, but if you're not in class, let me show you the demo of this. So what we're going to do in class is start with an 8.5 across by 11-inch piece of construction paper. Okay, everybody's going to get a piece of this. And my instructions to them are going to be to cut squares from the corners of each, well, cut a square from each corner. So what that's going to look like, I've already demoed it here. I decided to cut 2-inch squares from my corners. So I just took a ruler and I measured 2 inches off the corner each direction. I did that over here on the right. I did that down here on the bottom left and the bottom right. So I'm actually going to do this right here on the video. I'm going to cut these out so that you can really get a sense of what's happening here, because for some people this is a little hard to visualize without actually doing it. I know it is for me. So I'm cutting, I'm not being exact here. I just want to give you an idea of what this box would look like. So again, I'm just cutting 2-inch squares out of the corners, but I have no idea if that was a good choice. Maybe I should have made them 1-inch squares or 2.5-inch squares. I don't know yet. Okay, so this is what you've got left over now. Okay, now what I'm going to do is fold up the sides. So I'm going to bend this in and crease it. I'm going to crease my bottom, crease my sides here, and the final side, crease that. And then I've got some handy dandy tape here, and what I'm going to do is tape together, if I can grab it here, the sides of my box. Again, I'm just trying to give you an idea here. I'm going pretty quickly, so this is not going to be the prettiest box you've ever seen. My tape is not working with me either. Okay, so we'll tape this together here. It's getting there. My tape has stuck itself to the desk. Okay, we'll tape that together. And finally, the last side, we'll tape this together. And you've got yourself a box. So there it is. So if you, not very nice, but you get the gist here. So I just cut those corners, folded up the sides, taped the box together. Okay, but how much does this box hold, and is it the most that it can hold? Have I optimized the dimensions of this box so that it has the most volume? Well, that's what calculus and the first derivative test are going to help us figure out. So back to your worksheet now. I'm going to solve this problem here, and actually I want to show you one more thing. What I did here on this separate sheet of paper, and you can feel free to put this right on your note sheet. What I did is I redrew the 8.5 by 11 inch piece of paper, and I modeled cutting out the squares from each corner. And what I want to talk about is the volume now. So the side that was 8.5 inches, so the top and the bottom, so from here to here, it used to be 8.5 inches before I cut anything out. But what happened is I cut X inches here and X inches here. So now instead of having 8.5 inches, I actually have 8.5 inches minus two sides, each at length X inches. So my new length from here to here is 8.5 minus those two X's. My width used to be 11 inches before cutting anything, but then I took X and X off of this side, so what used to be 11 is now 11 less 2 X's. So my new width is 11 minus 2X. Now my height, you can't get from this, but when you envision creasing, I creased this, and I folded this up. So what was sitting here as an X value just got bent upward and became the height of the box. So the height of the box, which right here, if you look here, so here's my box, this height coming up here is X, because that's the value that was bent up, and that was what I had as what I cut from my corner. Okay, so using that, I'm going to bring this back to my worksheet. So for volume, what I'm going to do is write my volume equation as length, which I said was 8.5 minus 2x, times width, 11 minus 2x, times height, which is just x. I'd like to clean this volume equation up by foiling. So I'm going to foil these two. So 8.5 times 11 is going to be 93.5. 8.5 times negative 2x is negative 17x. Negative 2x times 11 is negative 22x. And of course, negative 2x times negative 2x is positive 4x squared. And this is all still times the height, which is x. Next, I'm going to combine like terms, so I have 93.5 minus 39x plus 4x squared, and this is still times x. So now I'm going to go ahead and distribute the x through, and I'm actually going to rewrite the order so that my highest degree, or my highest exponent, which is the degree of the polynomial, is first. So x times 4x squared is going to give me 4x cubed. X times negative 39x is negative 39x squared. And then x times 93.5 is positive 93.5x. So this is the volume. This is a volume of a box made from an 8.5 by 11 inch piece of paper, and it's leaving that X open for any size squares you want to cut. I cut 2-inch squares, but this X means I'm leaving it open to being able to cut any side length. Now, I want to optimize / maximize volume. I want this volume to be the biggest, and so that my box holds the most. So interestingly enough, we've just been studying how to find maxes and mins of graphs that we have equations to. So I'm basically just going to take this volume equation and take it through the steps we've been doing to find the maximum volume. So I'm going to start that by finding the derivative and setting it equal to 0. So v prime will equal the derivative, which would be 12x squared minus 78x plus 93.5. And I want to see when that slope is 0, because when the slope is 0, I'll be at my high point or my low point. So I'm setting that equal to 0. Now to me, because of this decimal in the end, this does not look factorable to me. So I'm going to have to go to prior knowledge of the quadratic formula to solve this. So let's take it up here for space, and let's run the quadratic formula. In order to run the quadratic formula, I'm going to need to identify my A, my B, and my C. My A is 12, my B is negative 78, and my C is 93.5. Just to review the quadratic formula will solve for x, and it will look like this. The opposite of b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. So I'm going to go ahead and plug my values in. So x equals, the opposite of b would be positive 78 plus or minus the square root of negative 78 squared minus 4 times 12 times 93.5 all over 2 times 12. I'm going to keep solving, and what I like to do, what's easiest for me, is I do the discriminant all in one step. So let me bring my TI in here. I would like to just simply type in altogether what's under the root. So I'm going to do quantity negative 78 squared minus 4 times quantity 12 times quantity 93.5, and that gives me 1,596. So I'm going to just go right to that step, 1596. And this is all over 2 times 12 is 24. Now, what I will check, I always check if that is a perfect square. 1,596 is not a perfect square. So for accuracy of my answer and to leave my answer unrounded to the final step, I'm actually going to split this problem now into 2 different parts. First, I'm going to address the plus. So one of my x values is going to be 78 plus the square root of 1,596 all over 24. And then the other x value, I'll address the minus, will be 78 minus the square root of 1,596 all over 24. And then I will go ahead and put those into my calculator. So coming down here, this top problem here, x equals. Okay, I'm going to put this in my calculator, clear that. So I've got 78 plus the square root of 1,596. I'm going to hit enter on that, divide by 24, and I'm getting a final answer there of 4.915 if I round to thousands. So 4.915, or if I put this one into my calculator, I'll do that down here. Let me show you another way to do this as well. If you have the alpha y equals feature on your calculator, you could put it in as a numerator over denominator. It would look like this, 78 minus the square root of 1,596 over 24. And there I'm going to get 1.585. Okay. Now, it looks like I have 2 answers, but actually, this answer right here ends up being extraneous, and I'm going to show you why. If you cut squares 4.915 inches from the corners, it's actually going to mess with your length. If you look back at your length, the length here, once we cut the squares out, was the 8.5 minus 2x figure. If you take 8.5 minus 2 times 4.915, you end up getting negative, let me see what it is here. Thought I had that. Yeah, negative 1.33. Well, that doesn't make any sense. You're not going to be able to make a box if your side length is negative. So that is why we're going to have to throw out that answer. But if you cut your squares 1.585 inches, That will work. It will keep your length positive and your width positive. So we're going to go with that. So let me put inches on here, and this is going to be our critical point. Now, to make sure that it is, we need to make a chart like we always do. And I'm going to actually go to my next video to do that. This video is getting a little bit long, so tune in to the second video under optimization to finish this problem.